Upper Little Tennessee River Basin, autumn of 1763. While neighboring Cherokee families quickly dug standard open hearth pits for the approaching winter, hunter and craftsman Tali was still working in his eighth week of preparation, coating his below-ground fire pit with a thick layer of white clay mixed with crushed mussel shells. His fellow townspeople called it clay crazy. The tribal elders questioned why he wasted time on potter's work when simple mud-lined pits had heated winter houses for generations. Then the brutal freeze of 1763 arrived. Temperatures plummeted to 8 degrees below zero and stayed there for 39 consecutive days. The harshest cold in living memory that would test every heating method in the middle towns. Standard open hearths consumed double their expected wood, while house interiors still dropped below freezing. Families woke to frost-covered blankets and spoiled food stores. But Tali's clay-coated fire pit radiated steady heat through the night, keeping his house warm with 70% less fuel, while others burned through their winter wood supplies. What did this Cherokee craftsman understand about thermal mass and heat retention that even modern fireplaces fail to achieve? The morning mist clung to the Little Tennessee River as Tali knelt beside the circular hole he had been excavating behind his winter house for the past 3 weeks. At 38, he possessed the steady hands of a skilled woodworker and the methodical patience that had served him well as both hunter and seasonal trader with the Creek settlements to the south. But this autumn project had drawn more attention than he preferred from his neighbors in the Middletown's region. His brother Chano crouched beside the pit, measuring its depth with a marked hickory staff. 3 feet exactly, the 22-year-old confirmed, his breath visible in the crisp October air. The circular excavation stretched 4 feet across, its walls carved straight and true through the red clay soil that characterized this section of the Appalachian foothills. Chano had spent the previous day helping haul out basket loads of earth, though he still questioned the logic behind his older brother's design. The smoke will settle in such a deep pit, Chano said, echoing concerns he had heard from other young men in the settlement. Uncle Taliga says the fire needs to breathe upward, not hide underground like a root cellar. Tali continued smoothing the pit walls with a flat stone scraper, his movements deliberate and practiced. The memory of the winter of 1757 still burned clearly in his mind, the season when his father's standard hearth had failed to keep their house above freezing, when their stored squash had turned to mush and ice crystals had formed on the interior walls, despite burning wood every 2 hours through the night. That winter had taught him that accepted methods sometimes proved insufficient when nature tested them beyond normal limits. "The fire will breathe differently," he replied, setting down his scraper and reaching for the first load of sandstone cobbles that Losi, his 26-year-old cousin, had collected from the creek bed. "But it will also remember the heat longer." Elder Nindalu approached from the direction of the council house, his weathered face creased with the skeptical expression that had become familiar over the past month. At 62, he carried the authority of 3 decades overseeing winter preparations for the settlement, and his opinion influenced how other families approached their own heating arrangements. "Tali," the elder said, stopping at the edge of the excavation, "you work like a potter preparing clay, yet winter will test you as a householder feeds fire. My pit has warmed my family through 15 winters using the method my father taught me. Why do you choose this path?" The question carried weight beyond mere curiosity. In Cherokee society, innovations that departed significantly from established practices required justification, particularly when they demanded extra labor and resources that could be allocated elsewhere during the critical pre-winter period. Tali understood that his neighbors viewed his project as potentially wasteful, consuming 8 full days of work that could have been spent hunting or gathering nuts. He began placing the creek stones into the bottom of the pit, creating a level foundation 6 inches thick. Each stone had been selected for size and stability, forming a drainage layer that would prevent moisture from seeping upward into the fire area. "I listen to the potters speak of clay that holds heat after the firing ends," he said, lifting another stone into position. "Their vessels stay warm to the touch long after they leave the flames. I wondered if the same principle might serve a winter hearth." Nindy Lou shook his head slowly. "Clay pots are small things, easily heated through. A house requires different fire, constant feeding, strong draw for the smoke. You risk your family's warmth on potter's wisdom." The criticism reflected broader concerns circulating through the settlement. Householder Una Su, whose dwelling stood only 50 paces away, had been particularly vocal about the unconventional approach. At 45, Una Su commanded respect as an experienced woodcutter who typically harvested 4 full cords of oak and hickory each autumn, the standard amount required to heat a Cherokee winter house through the cold months. His own hearth pit, dug to the traditional depth of 2.5 feet with a diameter of 4.5 feet, had served his family reliably for 7 consecutive winters. "Why waste extra days on such deep digging?" Una Su had asked the previous week while observing the excavation progress. "A brisk fire fed every hour will warm any house. The work should go toward cutting more wood, not playing with mud and stones." Despite the mounting criticism, Kaya Tali continued his methodical preparation. His travels as a trader had taken him to Cherokee settlements in the mountains of western Carolina, where he had observed variations in hearth construction adapted to different climates and fuel availability. In one town near the headwaters of the Tuckasegee River, he had seen winter houses with fire pits lined with thick clay coatings that seemed to radiate warmth even when the flames burned low. The technique had intrigued him, though the potters there had been reluctant to share details with an outsider. The key insight had come during his summer visits to the Unacre clay deposits in what would later become Macon County. The Cherokee had long prized this particular white clay for its properties in pottery making, but Kayatali had noticed how the material retained heat differently than ordinary mud when fired. Crushed mussel shells, traditionally added to pottery clay as temper to prevent cracking during firing, might serve the same purpose in a hearth lining subjected to repeated heating and cooling cycles. Over the following days, he mixed his coating material with careful attention to proportions learned from watching the settlement's most skilled potters. The white Unacre clay formed the base, combined with coarse sand comprising 30% of the volume to provide structure, and crushed mussel shells making up 15% to serve as temper. The shells, gathered from the riverbank and broken into pieces roughly 5 millimeters in size, would prevent the clay from cracking when subjected to the intense heat of a hardwood fire. Applying the mixture required patience and precision. Working with Cheno and Losi, Kaya Tali pressed the clay coating against the vertical walls of the pit in layers, building up a thickness of 2 full inches around the entire circumference. The coating needed to cure for several days before the crucial burn-in process that would transform it from simple clay into a ceramic-like shell capable of storing and slowly releasing thermal energy. As October drew toward its close, and the first frost warnings appeared in the changing leaves, Kaya Tali prepared for the final step that would either validate his unconventional approach or expose it as misguided experimentation. The burn-in process would require maintaining a hot fire for 24 continuous hours, gradually raising the temperature of the clay lining until it reached the point of vitrification. Success would create a thermal mass capable of storing heat and releasing it slowly over many hours. Failure would leave his family facing winter with a damaged hearth and depleted wood reserves. The settlement watched and waited, traditional wisdom poised against individual innovation, as the first snow clouds gathered over the Appalachian peaks. The cold arrived with unprecedented ferocity on the 7th day of November, 1763. What began as typical autumn temperatures plummeted overnight to 8 degrees below zero, and unlike the usual pattern of brief cold snaps followed by warming periods, the frigid air mass settled over the Little Tennessee River Basin and refused to move. For 39 consecutive days, nighttime temperatures remained locked below zero, while daytime highs struggled to reach 14 degrees above. By the 10th day of the freeze, the standard heating methods throughout the Middletown settlement began showing strain. Una Sue found himself feeding his open hearth pit every 2 hours instead of his usual 4-hour intervals, yet his house interior measured only 32 degrees at dawn, despite burning through nearly twice his expected wood allocation. The open design of his traditional pit, with its direct upward chimney draft, created a relentless draw that pulled heated air from the house, while simultaneously drawing cold air in through floor gaps and doorway seams. Keatali's clay-lined pit performed differently from the first night of extreme cold. After banking his evening fire at sunset, he covered the coals with a thin layer of ash and observed the temperature of the ceramic lining with his hand held 6 inches above the surface. The clay registered intense heat, approximately 190 degrees by his estimation, based on pottery firing experience, and continued radiating warmth throughout the night. When Chano checked the interior temperature at dawn using a simple method of observing water behavior in clay vessels, their house maintained 52 degrees, while frost formed thick patterns on the interior walls of neighboring dwellings. The fundamental difference lay in thermal mass storage versus immediate heat dissipation. Unasu's traditional hearth, lined only with 4 inches of ordinary mud plaster, possessed insufficient mass to retain significant heat once the active fire diminished. The open pit design, inherited from generations of Cherokee winter house construction, had evolved during periods of moderate cold when wood remained abundant and constant feeding presented no hardship. But the unprecedented freeze of 1763 exposed the limitations of a system designed for different conditions. Meanwhile, Keatali's ceramic shell, weighing approximately 450 kilograms of fired clay, sand, and shell temper, functioned as a massive heat storage device. During active burning, the 2-inch thick lining absorbed thermal energy throughout its structure. When the fire reduced to coals, this stored heat gradually transferred back into the house interior over 6 to 8 hours, maintaining comfortable temperatures without constant wood feeding. Elder Nindilu visited on the 15th day of the freeze, his usual skepticism tempered by the practical realities affecting his own household. His traditional pit, constructed according to methods passed down through his family, for 3 generations required wood feeding 4 times each night to prevent interior temperatures from dropping below freezing. Even with this intensive schedule, ice formed in his water storage vessels by morning, and his family slept under multiple layers of fur and woven blankets. "Your fire burns differently than mine," the elder observed, standing near Keatali's pit, where the clay lining still radiated detectable warmth from the previous evening's fire. "The heat seems to live in the walls after the flames sleep." The physics principles at work, though unknown to 18th century Cherokee science, followed predictable thermal dynamics. The ceramic lining's thermal conductivity of approximately 1 2/10 watts per meter Kelvin allowed gradual heat transfer rather than rapid dissipation. Its specific heat capacity enabled the material to store roughly 900 joules of energy per kilogram per degree of temperature rise. With 450 kilograms of thermal mass heated to 200 degrees above ambient temperature, the system could store and slowly release approximately 80,000 kilojoules of energy equivalent to the heat output of burning 22 pounds of hardwood. The below-ground positioning provided additional advantages that became apparent as the freeze intensified. Traditional Cherokee hearths, built at floor level with tall smoke outlets, created strong convective currents that enhance both heat loss and cold air infiltration. Keatali's sunken pit reduced these air movements by approximately 45%, while the surrounding earth provided insulation that further minimized thermal losses. By the 20th day of sustained cold, the settlement's wood consumption patterns revealed the stark differences between heating systems. Unasu had burned through 1 2/10 cords of his winter supply, forcing him to venture into frozen woodlands to cut additional fuel. His stored winter vegetables, kept in baskets near his traditional hearth, began showing signs of freeze damage as house temperatures fluctuated wildly between active firing and the cold periods between wood feeding. Keatali logged his consumption carefully, 4/10 of a cord consumed over the same 20-day period. His stored squash and dried corn, positioned on raised platforms near the consistently warm clay walls, remained well preserved and showed no signs of freeze damage. The steady thermal environment created by the ceramic mass proved ideal for food storage, maintaining temperatures just above the critical freezing point that damaged cellular structure in plant materials. The crisis deepened as December progressed without the expected warming trend that typically broke winter cold spells in the region. Households throughout the settlement faced difficult choices between fuel conservation and maintaining livable interior conditions. Some families began sharing houses to pool their heating resources, while others rationed their wood burning to preserve supplies for potential months of continued cold. Unasu's situation became particularly precarious when a coating of ice formed on the interior walls of his house during a night when he attempted to stretch his wood supply by feeding the fire only twice. The interior temperature dropped to 18 degrees, and his youngest child developed a persistent cough that worried his wife. The following morning, he approached Keatali with questions about clay lining techniques, though his pride prevented him from directly requesting instruction. The fundamental lesson emerging from the sustained freeze involved understanding heat storage versus heat generation. Traditional Cherokee winter heating had relied on continuous fire feeding to maintain warmth, an approach that worked effectively when moderate cold allowed for manageable wood consumption. But extreme conditions revealed the superior efficiency of thermal mass systems that captured and stored heat energy during active burning periods, then released it gradually during non-burning intervals. As the freeze entered its 4th week with no signs of breaking, the settlement faced the reality that their traditional heating wisdom might prove insufficient against nature's most severe tests. The wind-driven snowstorm struck on the 10th day of January, 1764, depositing 30 inches of snow across the Little Tennessee River basin in 18 hours. What transformed a severe winter into a survival crisis was not merely the snow depth, but the drifting patterns that blocked access to established wood-cutting areas and isolated individual households from their fuel supplies. The storm's aftermath left the settlement facing fuel shortages, just as the sustained freeze entered its 10th week with no indication of breaking. Maguwa discovered the true extent of his predicament on the morning of January 13th. The 49-year-old householder had maintained his family through the early weeks of extreme cold by extending his wood-cutting expeditions and rationing his hearth feeding to 3 times per night instead of the continuous burning that other families employed. But the storm had blocked the path to his primary woodlot with drifts that reached above his waist, and his remaining fuel supply consisted of less than 2 weeks' worth of split oak and hickory. His house interior, heated by a traditional open pit measuring 3 feet deep and 5 feet across, dropped to 15 degrees during the first night of reduced wood burning. By sunrise on January 14th, ice had formed in the water vessels kept near his hearth, and his stored winter vegetables showed signs of cellular damage from repeated freeze-thaw cycles. His wife wrapped their two youngest children in doubled blankets, but the inadequate heat retention of the mud-lined pit meant that even minimal fuel conservation resulted in dangerous interior conditions. 3. Other households faced similar situations as drifted snow made wood gathering impossible and existing supplies dwindled. The settlement's traditional approach to winter heating, continuous wood feeding of open hearths designed to burn hot and draw strongly, proved catastrophic when fuel became scarce. Families were forced to choose between burning their remaining wood quickly to maintain warmth or rationing it carefully and accepting dangerously low interior temperatures. Unasu attempted a compromise strategy by feeding his fire only during the coldest nighttime hours and allowing it to die during the day, hoping that activity and shared body heat would compensate for reduced burning. The result was interior temperature swings from 28 degrees during active burning to 12 degrees by mid-morning, creating conditions that froze his stored food supplies and left his family at risk of hypothermia. The fundamental flaw in traditional Cherokee winter heating revealed itself starkly during this fuel shortage. Open pit hearths with strong updrafts required continuous wood input to maintain warmth because they lacked thermal mass to store heat energy. When fuel became scarce, families faced an impossible choice: burn their remaining wood supply quickly and face complete fuel exhaustion, or ration carefully and endure potentially fatal cold. Keya Tali's ceramic-lined pit continued functioning effectively despite the fuel crisis. His household's consumption during the critical 2-week period of heaviest snow measured 0.3 of a cord, approximately 70% less than what neighboring families required during the same period. The clay lining's thermal storage capacity meant that a single evening fire, burned hot for 30 minutes and then banked under ash, provided adequate heat for 12 to 14 hours. On January 23rd, the crisis reached its breaking point when Ma Gu-wo's household ran out of split wood entirely. With interior temperatures dropping toward lethal levels and no access to additional fuel, he approached Keya Tali, requesting temporary shelter for his family of 4. 2 other households faced identical situations within 24 hours, creating a refugee crisis within the settlement as families lost the ability to heat their homes. Keya Tali's house, designed for his immediate family of 5, suddenly accommodated 12 people during the most severe cold period of the winter. The ceramic hearth system proved capable of heating the expanded occupancy load, though it required adjustment in firing techniques. Instead of the single evening fire that had sufficed for his family, he now burned 2 fires daily, one at sunset and another at midnight, with each fire session consuming approximately the same amount of wood that traditional hearths burned in 1 hour. The crowded conditions revealed additional advantages of the thermal mass heating system. Traditional Cherokee winter houses with open hearths created uneven heating patterns, with temperatures varying significantly based on proximity to the fire pit. Families typically arranged their sleeping areas in concentric circles around the hearth, with the warmest positions reserved for elders and children. But rapid heat loss through the smoke outlet meant that even favored positions near the fire experienced significant temperature drops during the hours between wood feeding. The ceramic-lined pit created more uniform heating distribution because the clay walls continued radiating stored heat throughout the night. Sleeping platforms positioned around the pit's perimeter all received consistent thermal radiation, eliminating the competition for prime heating positions that characterized traditional arrangements. The 12 refugees were able to arrange themselves throughout the house interior without anyone suffering from inadequate heat exposure. Food preservation presented another critical advantage during the extended housing arrangement. The consistent temperatures maintained by thermal mass heating prevented the freeze-thaw cycles that had damaged stored vegetables in houses with fluctuating heat output. Maguwa's family arrived carrying their remaining winter provisions, approximately 40 pounds of dried corn and 15 pounds of stored squash, which remained well preserved throughout their 10-day stay despite the crowded storage conditions. The extended community arrangement also demonstrated fuel efficiency advantages at larger scales. Heating 12 people in one thermally efficient house required approximately the same wood consumption as heating 3 people in a traditional house, revealing potential applications for community heating during extreme weather emergencies. The ceramic hearth's ability to store and slowly release large quantities of thermal energy made it economically feasible to provide adequate warmth for expanded occupancy without proportional increases in fuel consumption. By early February, as the storm-deposited snow began settling and some access to woodlots became possible, the 3 refugee families gradually returned to their own dwellings. But the experience had provided unmistakable evidence of the superior performance of thermal mass heating during fuel shortage conditions. Traditional Cherokee winter heating wisdom, developed during generations of normal winters with adequate fuel supplies, had proven inadequate when extreme conditions tested the fundamental assumptions underlying accepted methods. The crisis had transformed community perceptions of innovation versus tradition, preparing the ground for broader acceptance of techniques that challenged established practices. The spring thaw began on the first day of March, 1764, bringing immediate complications that further exposed the limitations of traditional Cherokee heating systems. As daytime temperatures climbed toward 45 degrees, households throughout the Middles, town settlement faced the challenge of transitioning from winter heating to spring ventilation without losing control over their interior environments. Unasu's house exemplified the problems inherent in open hearth design during seasonal transitions. His traditional pit, optimized for strong updraft during cold weather, created excessive air circulation when exterior temperatures rose. On March 3rd, he opened his smoke outlet wider to clear accumulated winter soot, but the increased ventilation rapidly dumped the stored heat from his house interior. Within 2 hours, his interior temperature dropped from a comfortable 60 degrees to 42 degrees, forcing him to restart his fire during what should have been a period of reduced heating needs. The volatile temperature swings characteristic of traditional Cherokee heating became most apparent during the transitional weeks of early spring. Houses heated by open pits experienced rapid thermal fluctuations as occupants attempted to balance ventilation needs against heat retention. Many families found themselves alternately overheating during active burning periods and cooling too rapidly during ventilation, creating uncomfortable living conditions that persisted well into March. Kayatali's ceramic-lined system demonstrated superior thermal regulation during the spring transition period. The massive clay walls, which had absorbed and stored heat throughout the winter months, now moderated temperature changes by releasing stored thermal energy gradually as exterior conditions warmed. His house interior maintained a steady 58 degrees throughout early March without active fire burning, the ceramic mass continuing to provide gentle heating as it slowly equilibrated with the warming environment. The moderation effect proved particularly valuable for food storage during the critical spring period when temperature fluctuations could damage preserved provisions. Traditional Cherokee winter houses often experienced freeze-thaw cycles during spring nights that could spoil stored corn and squash just when fresh food sources remained unavailable. Households that had carefully preserved vegetables through the harsh winter sometimes lost significant portions of their supplies during the unpredictable temperature swings of March. Kayatali's stored provisions, kept on raised platforms adjacent to the thermal mass walls, remained at stable temperatures throughout the transition period. His 200 pounds of dried squash showed no signs of moisture damage or cellular breakdown that characterized storage losses in houses with fluctuating temperatures. The consistent thermal environment created by gradual heat release from the ceramic lining provided ideal preservation conditions that extended the usability of winter food stores well into the spring season. On March 8th, Elder Nindilu conducted his first systematic examination of both heating systems as the winter crisis definitively ended. Walking between Unasu's house and Keatali's dwelling, he could detect the temperature differences immediately upon entering each structure. Unasu's interior felt sharp and variable, warm near the recently fed hearth, cool near the walls, with drafts of cold air entering through the smoke outlet and floor seams. Keatali's house maintained gentle, even warmth that seemed to emanate from the walls themselves rather than from any central heat source. The elder knelt beside Keatali's hearth pit and examined the ceramic lining that had performed throughout the winter without failure. The 2-inch coating of clay, sand, and crushed mussel shells remained intact with no visible cracking or spalling despite months of repeated heating and cooling cycles. The tempering materials had successfully prevented the thermal shock fractures that often damaged pottery subjected to rapid temperature changes, validating the application of ceramic techniques to hearth construction. In contrast, Unasu's traditional mud-lined pit showed significant deterioration from winter use. The thin plaster coating had cracked in multiple locations, and sections of the wall had collapsed, where repeated heating had dried and shrunk the mud beyond its structural limits. The pit required complete rebuilding with fresh mud plaster, an annual maintenance task that Cherokee households typically performed each autumn. The durability advantages of ceramic lining became apparent as other traditional hearths throughout the settlement showed similar deterioration. Mud plaster, adequate for single-season use, lacked the structural integrity to withstand repeated thermal cycling without maintenance. The ceramic coating, fired in place through the burn-in process, had achieved the hardness and thermal shock resistance of pottery, creating a permanent heating surface that required no seasonal rebuilding. Archaeological evidence from Cherokee winter house sites would later confirm the transition toward more sophisticated hearth construction during the mid-18th century. Excavations revealed increasing frequency of clay-lined fire pits, with evidence of in-place burning that suggested ceramic coating techniques. The archaeological record indicated that innovations like Keatali's method gradually spread through Cherokee communities, though the adoption process typically required several years of demonstration before new techniques achieved widespread acceptance. Elder Nindilu's examination extended to fuel consumption analysis based on woodpile measurements from throughout the winter. Unasu had consumed 3 3/10 cords of hardwood, approximately 15% above the traditional allocation for a house of his size. The prolonged cold had forced him to burn beyond normal rates, and his supply had required supplementation through dangerous woodcutting expeditions during storm conditions. Keatali's total consumption measured 9/10 of a 1 cord for the entire winter period from November through March. The 72% reduction in fuel requirements represented not merely an efficiency improvement, but a fundamental transformation in heating strategy from continuous wood burning to thermal energy storage and gradual release. The spring assessment revealed the traditional Cherokee heating wisdom, developed during generations of moderate winters, had been tested and found insufficient by the extreme conditions of 1763 to 64. Innovation derived from ceramic techniques and thermal mass principles had proven superior under stress conditions, establishing the foundation for broader adoption of advanced heating methods throughout the Cherokee settlements of the Appalachian region. The spring corn planting ceremony of 1764 provided the first formal opportunity for Keatali to share his heating innovations with the broader Cherokee community. On the 20th day of March, as families gathered to discuss agricultural preparations and household improvements, Elder Nindi Lu approached him with a request that carried significant cultural weight. The elder, whose authority had initially opposed the ceramic hearth experiment, now sought detailed instruction in the construction methods that had proven superior during the harsh winter. Kaya Tali began his teaching by emphasizing the critical importance of proper clay selection and preparation. Not all clay possessed the thermal properties necessary for effective hearth lining. The material required specific characteristics that combined heat retention with structural durability. The white unacre clay deposits located in the mountainous regions of what would later become Macon County provided the ideal base material, but accessing these deposits required organized expeditions during late summer when river levels allowed safe travel to the quarry sites. The mixing process demanded precise ratios that Kaya Tali had refined through careful observation of pottery-making techniques. The base clay comprised 55% of the mixture by volume, providing the primary heat storage capacity and structural matrix. Coarse sand, screened to eliminate particles smaller than 1 millimeter, formed 30% of the mixture and prevented excessive shrinkage during the drying and firing process. Crushed mussel shells, broken to uniform pieces approximately 5 millimeters in diameter, constituted the remaining 15% and served as temper to prevent thermal shock cracking during rapid temperature changes. Uncle Tali Ga, the experienced potter whose techniques had inspired the original innovation, joined the instruction session to demonstrate proper shell preparation methods. The mussel shells required careful crushing to achieve uniform size distribution. Pieces too large created weak points in the ceramic matrix, while fragments too small failed to provide adequate thermal shock resistance. The crushing process involved placing shells between flat stones and applying controlled pressure to produce angular fragments with maximum surface area for bonding with the clay matrix. The application technique required systematic approach that built the lining in successive layers rather than attempting to coat the entire pit wall simultaneously. Kaya Tali demonstrated the proper consistency of mixed material, wet enough to adhere firmly to vertical surfaces but dry enough to maintain its shape without slumping. Working with dampened hands, he pressed the mixture against the pit walls in horizontal bands, ensuring complete adhesion between layers and eliminating air pockets that could cause structural failure during firing. Losi, who had assisted with the original construction, explained the critical importance of the drying period between application and burn-in. The coating required 4 to 7 days of gradual moisture evaporation, depending on humidity conditions and ambient temperature. Rushing this process by applying heat too early would cause steam formation within the clay matrix, leading to explosive failure that could destroy the entire lining. Proper drying was indicated when the coating changed from dark gray to light brown and showed no visible moisture when scratched with a fingernail. The burn-in procedure represented the most technically demanding aspect of the construction process. Cheno, drawing from his experience monitoring the original firing, described the gradual temperature escalation that transformed ordinary clay into a ceramic shell. The process began with small fires using dry kindling to raise the pit temperature slowly over the first 6 hours. Too rapid heating would cause thermal shock that cracked the lining, while insufficient heat would fail to achieve the vitrification necessary for long-term durability. Maguwa, whose family had survived the winter crisis in Kaya Tali's house, committed to building the first replication of the ceramic hearth design. His enthusiasm for the project stemmed not only from the demonstrated heating efficiency, but also from the fuel cost savings that would reduce his household's wood-cutting labor by approximately 60%. The economic advantages of thermal mass heating extended beyond simple fuel consumption to encompass reduced labor requirements and improved food preservation outcomes. UNASU's decision to adopt the ceramic lining technique required overcoming significant personal and cultural obstacles. His traditional hearth had served his family for 7 consecutive winters before the crisis of 1763, and abandoning proven methods in favor of innovations required careful consideration of potential risks. However, his direct experience of fuel shortages and temperature control problems during the extreme winter convinced him that traditional approaches might prove inadequate during future severe weather events. The technical instruction expanded beyond individual household applications to encompass community-wide adoption strategies. Elder Nindilu recognized that organizing collective clay gathering expeditions would reduce individual labor costs while ensuring access to high-quality materials for multiple families. Similarly, coordinating burn-in procedures would allow experienced practitioners to assist novices during the critical firing phase when technical expertise proved essential for success. The knowledge transfer process incorporated modifications based on specific household needs and local material availability. Families with larger dwellings required proportionally larger thermal mass systems, while households with limited access to unacre clay deposits experimented with local clay sources supplemented with additional tempering materials. These adaptations demonstrated the flexibility of thermal mass heating principles when applied by practitioners who understood the underlying engineering concepts. Archaeological evidence from Cherokee sites throughout the Appalachian region would later document the gradual adoption of ceramic-lined hearth systems during the late 18th century. Excavations revealed increasing frequency of fire pits with vitrified clay coatings and evidence of systematic burn-in procedures, suggesting that innovations like Kayatali's method spread throughout Cherokee communities over multiple decades. The archaeological record indicated successful adaptation of the technique to diverse environmental conditions and household configurations. By autumn of 1764, 10 households in the Middletown settlement had constructed ceramic-lined hearth systems based on Kayatali's instruction. The widespread adoption represented a fundamental shift in Cherokee winter heating strategy from continuous fuel burning toward thermal energy storage and controlled release. Traditional heating wisdom, tested and found insufficient by extreme conditions, gave way to engineering approaches that offered superior performance during challenging circumstances. The innovation established a pattern of technological development that honored traditional knowledge while incorporating new insights derived from careful observation and systematic experimentation, demonstrating that survival techniques could evolve without abandoning cultural foundations.